Calculus is the first mathematics that's really about how functions change. So a lot of what we've done so far is sort of a variation on the one thing that we know about understanding how a function changes. And that's if we have a linear function, we can compute its slope. We learned to call that rate of change. So we can apply this idea of finding slopes to think about how other kinds of functions change, even if they're not linear. So this idea of finding the slope at one single point instead of finding the slope like between the 2 points on a line. So we've talked about this calculation, average rate of change. This is going to be another one that goes on your important facts paper. Let's see if I can get this up here. So this is for that first big box in your notes paper. Average rate of change of the function f of x on the interval a to b is f of b minus f of a over b minus a. Notice a and b are inputs and f of a and f of b are outputs. This is essentially change in y divided by change in x, which we use to find average velocity, and we used to find your average growth rate the other day in class. So maybe you'll get a question like this one, this example. If you did, you'd think you were like, wow, super lucky, because there's not really that much calculus in it yet. But you might be asked to find the average rate of change of a function on an interval. So you're going to perform this computation. F of b minus f of a over b minus a. In this case, f of 3 minus f of 1 over 3 minus 1. So it's our job to kind of understand this function notation, right? So if f of x means x cubed minus x, it means I have to take the number 3 and I'm going to replace all the x's with it. So 3 cubed minus 3, take away 1 cubed minus 1, all over 3 minus 1. So then, interesting fact, if this were the free response section of the AP test, you could leave your answer like that. But in class, I'm going to simplify those so you can see. Just double check your answer. We get a result of 12. The average rate of change of f of x on the interval 1 to 3, in this case, is 12. There's an example in your textbook, and I recognize here I might not have checked your page number. In the last version of the textbook, it was page 87. It's going to be there in example 2. There's an example. We have a group of fruit flies, and we're interested to know how the population of the fruit flies changes over time. So we have some information there that tells us that on day 23 there are 150 fruit flies. On day 45 there are 340 fruit flies. And we can compute the average rate of change of the fruit fly population. So it's a little bit like what we practiced the other day with your average growth rate. We just want to make sure that we do that same computation, change in y over change in x, but make sure we keep the units with it. So I'm going to do the change in the output. So it's 340 minus 150. Notice the units on those numbers are fruit flies. And in the denominator, 45 minus 23 days. So 190 over 22 fruit flies per day. So I can just simplify that expression, 8.6 fruit flies per day. So 8.6 is the value, the fruit flies per day is the units. So all of that should have reminded you of what we did when we computed average speed. And if you're getting excited, you might remember that right after we talked about average speed, we wondered, what if I let those two time values get closer and closer and closer? If I could compute average speed over an interval that's like 0 time difference, I would compute instantaneous speed. So this is our goal. This is one of the whole reasons calculus came to be, is because mathematicians were interested in this idea of instantaneous rate of change. So remember my fruit flies? Now, in that case, I'm not actually going to have enough information, but can you imagine letting the time difference go from like being 22 days to being 1 day or 1 hour or 1 minute? You would find how fast the fruit fly population is changing at one moment. That's instantaneous rate of change. That's our whole goal. So I checked this page number. It really is page 88 in your book. So if you would pause here, I would like you to read page 88 in your textbook. And when we did the fruit fly problem, we took 2 points on the fruit fly population curve, and we found this, it's essentially the slope of the line containing those 2 points. When you find the slope of a curve using 2 points, that's called a secant line. A secant line touches at 2 points. So just for discussion, in case you don't remember your geometry vocabulary, what I just drew is a secant line to that circle because it touches the circle in 2 places. But if you let those points get closer and closer together, so you're not using 2 points but only 1 point, we have a name for that, and that's a tangent. So that's our goal, is instead of finding the slope of a secant line, let the 2 points on the curve get closer and closer together until it's 1 point. If I can find the slope of that line, that's the same as the instantaneous rate of change. So it's a little more difficult to define clearly what a tangent to a curve is. You guys talked about it in geometry. Tangent to a circle is kind of easy. It's got, because it has to be perpendicular to the radius. But check out this next page to talk about the tangent of the tangent to a curve. Okay, so these are 3 just curves that happen to have their tangent lines drawn in, so you can kind of start to get a feel for what it means, because I haven't really defined what a tangent to a curve is yet. I want to point out one thing. Notice this example here. You see this tangent line? It is tangent to the curve at whatever that x value is. It happens to also touch the curve again later. Now in a circle that would never happen. A tangent line touches the circle one place. This is still a tangent line, so that idea of saying it only touches the curve in one place doesn't really apply for other curves the way it did for circles. So we're going to try to make a definition for tangent line that doesn't use that idea. But I want you to think about this. You have a little bit of experience with an idea like this. What do you think would happen if you graphed these functions and their tangent lines and zoomed in on the graph? You're going to write your best description here of what you think, your prediction. What do you think would happen if you took these pictures and zoomed in at that place where the curve and its tangent touch? Okay, so what we want is the slope of the line that is tangent to the curve. We're going to do what we already talked about a little bit. We're going to take the point we care about, the point that we really want to use on the curve, and some other point that's not too far away. And then I'm going to think about letting that point get closer and closer. But for now, I'm just going to make sure I take the 2 points kind of close to each other. So imagine I have these 2 points. This is a comma of f of a, and a plus a little bit. I'm going to use h to stand for the little bit, and f of a plus a little bit. Could you write an expression for the slope of this secant line? You're going to write it here. Here's a hint. Since it's a slope, it's going to be a big fraction. Okay, so what you just wrote, which you should definitely check when you get to class, is called a difference quotient. See if you can figure out why we call it that. We're going to spend a lot of time, a lot of time in calculus evaluating difference quotients. So more on how to evaluate them in a second. Let me get this. Okay, so now I want you to imagine however small h was, not small enough. I want my points to be closer. So I'm going to do it one time. Not in blue, let's do green. I'm going to pick a point that is closer to P than Q was. And now I'm going to draw in a new secant line. I'm going to connect the same point P with my new green point. So the slope is clearly different. Question is, if we let my green point get closer and closer and closer to P and keep drawing that secant line, are we going to end up with one answer? So would you draw in 2 more secant lines just to practice kind of that idea, letting your point get closer and closer to P, and then I'm going to end this video with this big thought. As h gets closer and closer to 0, so as q gets closer and closer to p, the slope of the secant line is going to approach so much that it's essentially going to be equal to the slope of the tangent line. That's our big topic.